Hello and welcome to Calculus.
Oh, we're doing this again?
Yes, we are doing the calculus. Now, what is calculus? Calculus is...
From a textbook I have at home, I saw a broad definition of the mathematics of change, right?
Perfect. That's exactly what it is. Mathematics of change. So, in the heart of calculus, there is this mathematical concept called function. And we will be taking limits of functions in chapter 2. So as overview, chapter 2, limits, then chapters 3 and 4, we will take derivatives of functions, and then chapters 5 plus 6, most of the chapter 6 is in Calc 2, but whatever two sections we have would be integration. All of these on functions. Now, function is a concept you learn in pre-calculus. Some of you might have called it college algebra or algebra 2 or whatever name came up. But in some of your some course in your previous education, you learned about function. So now, what is the function? Function is a rule which assigns to each x in the domain a unique y in the range.
Y range?
Unique y in the range. The words that are important in this definition are obviously function, rule, domain, range, and the word unique, which is underlined twice. Okay. In order for us to do calculus, you need to be able to work with functions, which is what pre-calculus focuses on. This definition in this form will be a question on your first exam for 4 points. So go ahead, mess that up. I just told you. All right? Let's say question number 4. Cool? Yeah. So, or maybe number 3, whatever the question is, it says state the definition of a function. And you have to write this.
Function is a rule which assigns to each x in the domain a unique y in the range.
Exactly. So now, what does that mean? You are going to have a set, the input set, which is called domain. And that set will map, using the function, the element into a y, which is the output set, which we call the range.
Yep.
And the notation for this witchcraft is y equals f of x. So that's your notation. if you want the block diagram, you can think of function f as some kind of factory. The x comes in, the y comes out. An example. F of x equals 3x plus 6. So how much is f of negative 2? Well, if I replaced this x with negative 2, you will have to replace this x with negative 2 as well. So 3 times negative 2 plus 6 is negative 6 plus 6 is equal to 0. So if you want to use your block diagram, negative 2 comes in, 3x plus 6 operates on it, spits out 0 on the other end. So, function changes numbers. Technically, that's what it does. Function changes numbers. It changed negative 2 into a 0. Now, we understand this as ordered pair negative 2, 0, where negative 2 is for x and 0 is for y. And we can graph that. On xy coordinate system. When you draw big so you can see. Another suggestion that I would have is you guys to get
This is in the trash.
quad outside. For you guys to get a quad notebook, they're the same cost as the ones that you're using, but your graphs and drawings will be straight and equally spaced, and you will learn better if you have the grid rather than just lines. If you are planning on doing this, it's not gonna go well. All right, so please don't. So function is a rule which assigns to each x in the domain, which is input, a unique y in the range, which is the output. This means that under this rule, this input provides this unique output. Now we can do the experiment. If I assign f of x to be 2x squared minus 4, and I ask all of you to compute f of 3. Go!
I got it.
You got it?
Yeah.
What is it? What is it? 4? Huh?
Right over here.
14? Good? Alright. Did you all get 7? No. Good, because that would be wrong. What do you have?
14.
See? Everyone has 14.
Don't die.
Isn't that unique answer? Right? You get 14, and you get 14, and you get, I sound like opera, you get the house, and you get the house, and you get... the answer for everyone is 14, and that's that unique. It doesn't matter who computes it, where 2 times 3 squared minus 4 is 2 times 9 minus 4, 18 minus 4 equals 14. So we all have unique answer, and this is something that is a property of a function. And that's why the word unique is underlined twice. You can have the same definition without that word, but it's not a function, it's a relation. You see, in the world we live in, we have functions around us and we have relations as well. What would be an example of a relation? Well, example of a relation would be uniqueness is not present. When I teach right now, this image is visible on multiple devices. If you log into YouTube, you can see it there. You can see it displayed on a projector, and there it is on my screen as well. The output for my input is not unique, so that violates a function. Now, we do have a lot of curves that are not function, like a circle. Circle has x squared plus y squared equals, let's say, 9, 3 squared, 9. And if you draw a circle, this is a perfect circle. Your eyes are just terrible and you should check them out. No, I'm serious. People say it's not a circle. It is a circle. It's just check it out. The radius is 3 on this one. And if you draw a vertical line somewhere, you would see that for this input, let's say 2, you have 2 y values as the output. That is not allowed in a function because your output must be unique.
Oh.
So now, you okay?
Yes.
Okay. So your output must be unique. And as I said, in some cases, your output is unique. In others, it's not. So we separate those cases. Can you do calculus on equation of a circle? The answer is yeah, but it's not as nearly as easy and trivial as the regular functions that we are going to discover. So we all know what's going to happen every time I flip this switch. I did it already 10 times. I totally didn't, if anyone from administration is listening. And it's, as you can see, no one is worrying that I'm going to cause an earthquake or a hurricane or something. Never going to let it go. So, uniqueness of the outcome is something that it's very important for a function. Consider your primary communication method to your friends, which is no.
Voice?
No.
Phone?
It's part of the phone. Text messages, exactly, right? No one wants to talk to people. They're pesky, right? You just, text and then ghost. So, so now what is the text message? So imagine if the function did not exist in this world as a concept. And there are no unique assignments. You do have a keyboard present, right? There's the keyboard. And you push E, it prints J. You push delete K, it prints 8. Because anytime you push any of the keys, just a random assignment pops up. How annoying would it be to type anything? Right? You can't even use the delete key properly. So just to type in OK, you'd probably have to type for like 20 years before the O and K came back next to each other, right? Just on a random assignment on this many keys. So we hopefully agree that having a unique assignment, the unique outcome to the input, is extremely important. See, the switch that I was flipping earlier uniquely controls extra set of lights in this classroom. It is not going to randomly trigger lights anywhere else on this campus. It's not going to cause earthquake or start someone's car or whatever, right? So the idea is that the input will have the unique outcome, and we can observe that with the things that we have in our environment, right? With all the things that we deal with. Now, some are functions and others are not. And it is your job to sort which ones are functions, because, as I said, our calculus course will be dealing with functions primarily. So now, what are the important things about functions, other than computing functions, that you need to know in order to survive the course? So basic functions like polynomials, and then logarithmic, exponential, trigonometric, and all of that stuff. Then you need to know the way to graph these functions and shift them and flip them and all of that good stuff. And then you need to know how to combine functions and compose functions. And then a little bit about inverses. And then we can start calculus, right? So these are the, I totally skipped on trigonometric functions. So trig functions as well on the pile. So the goal of this talk is to just put all of that on the table and make sure that you are comfortable with those. Because one thing that calculus truly hates is you learning examples. Calculus is the course on concepts. The same concept will be applied to a polynomial, an exponential function, or a tangent function. And if you start learning example by example, you will quickly see that you don't have enough time. Not just the summer course, but any course you take. It is not possible to learn calculus example by example. You learn the concept, and then you apply that concept to whatever function is in front of you. I will repeat this later, but since I already said earlier that functions change numbers, as in this case over here, -2 is changed into a 0 on the output. In this case, number 3 is changed into 14. Calculus will be changing functions. Calculus will change function x squared into 2x. Or it will change function x squared into x cubed over 3. So calculus will be applied to a function to change the function because we need to compute certain things for our application, which you already mentioned. We want to measure the change, and because we want to measure the change, we'll need these functions. The functions describe the world around us. So now, what are the functions that we need to consider? What are the functions that we need to consider? Well, we'll start with, I forgot to, let me just write that in blood. Not a function.
So it was a relation, right?
Yes, it is a relation. Great. So, functions. Polynomial. say P of x equals a0 plus a1x plus a2x squared plus a3x cubed plus dot 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 plus an x to the n. Polynomials must be finite, and they are going to have the highest exponent term, and that one will be called leading term. So whatever this is, that's the leading term, whatever the highest exponent is. And also the order of the polynomial. So if your highest exponent is 5, order of polynomial is 5th degree. Now this polynomial contains a lot of the functions you guys learned. I'm going to keep writing and erasing now. If you have this much, it's a constant polynomial. Meaning, like, let's say y equals to 3. You can graph that as just a horizontal line through 3. So, if you have just y equals a number, that's the cheapest polynomial you can have. And it's just a constant polynomial. You can already see that there is no change in that one. It's always 3.
What's the subscript there? Is that a 0?
Yes.
All right.
So if you only have P of x equals to, let's say, a 3, or y equals to 3, in that case, it's a constant polynomial. Now, you might have two terms like this. Does anyone recognize this one?
What?
Yeah, but what is it? What's the name? Just say it. Linear. Very good. Your linear line, linear polynomial, y equal mx plus b is the way you learned it, where your b is a0 and m is a1 in our notation. And that's a linear polynomial, so that's your straight line that it's somewhere. So that's what we have there. We can include another term. What do we have then? Quadratic ax squared plus bx plus c, and we get that parabola shape. And then you can add another one and another one and another one. So technically, guys, all of the polynomials you learn in your algebra course are here in a single line. You did spend months on that, right? Linear lines and quadratics and cubic polynomial, figuring out the roots and all of those things. All of that in that first line. Next big group is going to be the group on exponential functions. Usually we write f of x is equal to a e. Now let's whatever. Or b to the x, whatever. So exponential, you have seen this. E to the x goes whee. E to the negative x. You know this as growth and decay. You did all of those problems or garbage or radioactive decay. Maybe metabolizing drug in the bloodstream. population, money, right? Growth of money on the account. So a whole bunch of that stuff, they all belong to exponential functions, and they all pass vertical line test, so they are functions, right? What's the inverse of exponential? Very good. Oops. Logarithmic function. So logarithmic functions, we have
log dx.
Yep. Rational function. When you divide two polynomials, they don't have to be polynomials, but usually they are, with q of x not allowed to be 0. Division by 0 tends to make explosions, so we stay away from that. We'll talk about that in a detail. Welcome to Calculus. Radical. Radical. Roll your R's. Can you? No? Noobs. No, there you go. So radical ones will have some root. You know, it doesn't have to be square root. It can be a third or a fourth or a seventh root. And this can be a function or something, so we'll talk about that. There it is, finally. Trigonometric ones. F of x equals sine x, f of x equals cosine x, f of x equals tangent x, f of x equals cosecant x, f of x equals secant x, and f of x equals cotangent x. 6 trigonometric functions. In Calc 2, you get to learn hyperbolic functions. Sine hyperbolic x, sine hyperbolic, cosine hyperbolic x, and so on. So it's going to come up. And then, so these are the heavy hitters, all right? Then we have those that show up, but they are not there all the time. Like absolute value. F of x equals absolute value of x. We'll talk about that. A whole bunch of piecewise functions, which are just these other functions stitched together. So these are the main functions. Are there more? Of course there's more. There's a book with 2,500 pages. It's called Mathematical Function by Abramovich. That book has polynomials on half of one page. 2,500 pages. Yeah. We're not even scratching the surface with this stuff. Not even. That's how many functions are there. But then the world is complicated. So, there we go. So, we have these functions. What do we need to know about these functions? You see, the trick is that we're going to learn we're going to learn many concepts in calculus, but whatever concept you learn in calculus applies to all of these. So you don't get to pick, I mean, you can if you want to, it's not good to do that. You don't get to pick your favorite and say, I'm going to learn everything about e to the x and completely ignore everything else, because no, right? So if you learn the concept, you learn the calculus concept, you learn that concept well, and then you apply that concept to all of these variety of functions. The hard way to deal with calculus is to try to learn examples for every single function, for every single calculus concept. That's a lot of hard drive space taken, right? And eventually it's going to squeeze someone's birthday or something, and then you're doomed forever. So to minimize memorization, to minimize the efforts, right? You get the concept, and then you apply that concept to all different functions, rather than learning each example separately, right? Minimizing the energy required. Just like why is the planet? We all agree over here, right, that the planet is round. Because if you don't, please, because buoyancy will protect you. No? Good. All right. Glad we cleared that up on day one. Why is the planet round? Sphere-like? Because every particle of the planet wants to be in its minimum energy state. And how you get to be in your minimum energy state? You want to be the closest to the center. Right? So the planet ends up being round because every point of the planet wants to be the closest to the center, which is in the middle of the planet. And now, that's called the minimum energy state, right? Like minimum energy state, the same for fat people, right? Goes the same, right? Minimum energy state, just round, sphere-like. No, I'm serious. So, polynomial, exponential, logarithmic, rational, radical, 6 trigonometric ones, and then absolute value, and then piecewise functions at the end. So now what do we want to do with these? Well, we first want to know how to compute values, which is what we did with polynomials over here. You want to know how to compute 2 to the 7th power. You want to know how to find log of what's log of 10,000?
4.
Excellent. Perfect. Log of 10,000 is 4 because there are 4 zeros.
Oh.
Because if there is no base specified, the base is 10. 10 to the 4 is 10,000. Good job. So these are the things that we will... Now I will have a talk about log functions. Don't freak out yet. There's no reason. What's the cosine of pi over 3? Excellent. That's good. Yes, it's 1/2. Great. So now that we cleared the calculations and basic functions, we also want to graph these. So remember how the syllabus and the course standards do not allow graphing calculator on the exam. Is there going to be graphing on the exam? Yes. So what are the functions that you need to know to graph by hand? Well, just these. Let's talk. Number 1, constant. Let's say y equals to 6. It's going to be your x. What happened?
Straight line.
Excellent.
Vertically or horizontally?
Horizontally. Because y equals 6. It has to be on the y-axis, and it's a 6. Number 2. Linear. y equals 2/3 x plus 1.
Well, maybe a line going up, starting line is up to be at 1.
Excellent.
And very 3 of the root going to the right, it's going to come up 2.
Yes, so we go 2 units up, 3 units over. We're going to end up at 3, 3. In this case, so y equals 2/3 x plus 1. Star this one. We do have an extremely important concept called the tangent line. You'll be sick of tangent lines. The whole chapter of tangent lines. So the tangent line problem is one of the central problems of Calculus 1. And tangent line is the straight linear line. So y equals mx plus b is going to be about 25% of your grade in this class. That's not exaggeration. Maybe I'm undershooting. So make sure you are dealing with the linear lines easy. Number 3, quadratic. Y equal x squared and all of its variations. Number 4, cubic. Y equal x cubed and all of its variations. And that's where we stop with polynomials. Generally those 4. Constant, linear, quadratic, and cubic. How many are there? Infinitely many, right? Can you have x to a 731st? Sure. Good luck graphing it. But yeah, you can have it. Number 5, exponential. Y equals e to the x, that's the purest form. Is that very special number that we are going to define in this class. You will know where it comes from. So we will have definition for e in Calculus 1. So far you just know it's irrational, it's special, it's old, and it's about 3, right? 2.7, 2718. Number 6. Logarithmic. We can just do the basic 1 ln x. That's the one that we usually see. It goes through 1 on the x-axis. Not sure if that's the graph. Well, good. All right. ln. Better? Good. Number 7. What was the order I went in? Order doesn't matter, but rational function. We'll go with the y equals 1 over x. You'll be sick of this function as well. It's good to explain a lot of concepts. And its partner in crime, another rational function, 1 over x squared. Also a good one. Number 9, radical. Usually for graphing we only stick with the square root of x. It starts at 0, 0. And it's that sideways parabola. Trig functions. Who's excited? Nah, I didn't see. 10. Y equal sine x. Just the first period. Bump up, bump down, ends at 2 pi, we're out. $11. Cosine x. So cosine x starts at 1, drops down to -1, goes back up to 1, from 0 to 2 pi. $12 is what? Very good. Tangent x. Now tangent x will have asymptotes at negative pi over 2 and positive pi over 2. Tangent has a period of pi. Sine and cosine have 2 pi. And the tangent one looks like x cubed. Yeah, that's x cubed. Well, no, it's not x cubed, but it kind of looks like it. And there's a reason for it that you will see why in Calc 2. Chapter 12. No, 11. Yeah, chapter 11. 13. Y equals cosecant x. Now, at this point, I should put the $100 bill on the desk and say, whoever runs to the board and draw this function, you keep the $100. That's what I thought. Look at that. Oh, you got it?
I have like an idea, but I don't want to.
Idea. You know.
Hey, what have you got to lose?
$100.
Isn't it just sine of x and just turn it 90 degrees?
Yes. I totally owe you $100 now. So easy, so easy. So what you do is you draw a sine function. Anywhere where sine hits the 0, you draw the asymptote, and then you invert these cups upside down, and then you get rid of the sine function.
Oh.
That's all it is. So now I want you to practice secant. So cosecant is a flip of a sine. Secant is a flip of common sense. Good, cosine. So you saw what I did, right? I drew the sine function, and then whenever the sine function hit the 0, hit the x-axis, I draw vertical asymptote. And then I flip the cups inside out. And then I delete the sine. So now you will draw cosine. You will draw vertical lines wherever cosine hits 0, and you will invert. Cups, you should get 3 pieces.
All right.
You have to do something. It goes up. Yes, please.
Yes, so let's see the remaining functions. Number 14 is y equals secant x. And as previously, we draw cosine function. We draw these asymptotes. Wherever cosine hits 0, we invert the cups, and then we get rid of the cosine. And there's your secant graph. Ends at 2 pi again. Easy peasy. Now, what's happening with the cotangent? Well, you can use the same technique. 15, y equals to cotangent x.
Yeah, it looks like
This one will be shifted from 0 to pi, 0 at pi over 2, and it will be like a negative x cubed going through pi over 2.
I thought it was going to look like y over y equals 1 over x.
It can. Sure, yes, it can.
Oh, really?
But it's going to end. So
All right.
1 over x does not cross the x-axis, but it resembles it. So that's your 6 trigonometric functions. Great. Now we need to focus on absolute values, and we have to focus on piecewise functions. So absolute value first. For absolute value,
What is that? Pi over 2 again?
yes. Good. Absolute value graphs. What's the absolute value? Absolute value of x, yes, but in general, what absolute value? In general. Amazing. Yes, 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 yes. So absolute value measures the distance of a number from 0. Consequence of that, absolute value always gives positive numbers. How far do you live from RVCC in miles? 15, great. So when you are home, RVCC is 15 miles away. How far is your home from RVCC? 15 miles. It's not negative 15, right? So if you're home, school is 15 miles away. If you're in school, home is 15 miles away. There's no negative, right? Distance is always positive value. So, absolute value measures the distance of a number to 0, which means, this is going to be weird now, but just play along, it will make sense eventually. If I have a 0, and I go 1, 2, 3, and then I go 1, 2, negative 3. I have absolute value of 3 is equal to, and absolute value of negative 3 is equal to. Now, when I am absolute value of 3, I make 3 hops to get to 0. When I am at negative 3, I make 3 hops to get to 0. Ready for the weird stuff? This 3 and this 3 are not the same 3. What? What do you mean 3 is not 3? No. The black 3 is a location on the x-axis. The red 3 is the distance. Huh? So if I say that, let's say it's 7 o'clock, 7 o'clock is not the same as 7 hours. So not all numbers are the same. And we will deal with this in calculus more often than you think. We are going to have...
So is it the red 3s on the number line?
What happened?
Say that the red and blue 3s are on values on the number line?
They are not values on that. They are distances. Red and blue are not numbers on the number line. Red and blue are distances.
All right.
The black numbers are numbers on the number line. So black numbers are locations. Colored numbers are measuring the distance.
Yeah.
Now, if I write something like this, and I ask you, we'll deal with this more, right? So if I write something like, this, and I ask you, what is this? What would you say?
I'd say it's a coordinate pair.
You would say coordinate pair. Would anyone else say anything else?
Point on the graph.
Point on a graph, which is the same thing, said differently, right? Anyone else? Because that's totally not what I was thinking about. I was thinking about the interval from 3 to 6. I was thinking about this interval. Right? Same notation. So we will have to be very specific as we go through this class. All right, great. So now that we understand absolute value and its dealings, it's time to do the graphs. You already offered that it's a V shape. Great. Y equals absolute x. V shape. Why? Why is it a V shape?
Can't be negative.
Good. There's nothing in a negative realm. Great.
There would be no negative value, just be a reflection of both sides.
So we reflect only what is negative, right? What is the original function? It's y equals x. And what does that look like? Looks like a 45-degree line. If I add absolute value, then this piece is no bueno anymore. We have to flip it up. Okay, let me get rid of the red so we can see it one more time if you missed it the first time. What I just taught you here is to graph anything absolute. I'm talking about absolute sine and absolute ln and absolute whatever the hell you have. If it dips below x-axis, you flip it up. This is the type of learning that calculus will ask you to do. You know the V shape. Great. That's for y equals absolute x. But we are going to have absolute sine x, right? And I don't want you to freak out, because it is as simple. If you know the basic function without absolute values, you draw that. And then, when you put the absolute values, whatever ended up below x-axis has to go up. And you kill it. So now, knowing this, what is the graph of y equals absolute sine x?
Okay, 2 humps.
2 humps, exactly. So, original sine function looks like this. You install absolute values, this hump goes up, and you're done. So now your question to practice, y equals absolute ln x. What is the graph for absolute ln x? Go. What happened? Please do. I'll get you the grid.
Sure.
Hold on.
Ah!
Stick with math. All right. What do you cross out? What do you draw? Excellent. Perfect. That's all it is. So it has this spike.
Here, I'll toss it back to you.
Oh, good. So for the absolute value, we are going to delete the piece below and draw the same piece up there, and there it is. So that's the absolute. So now this is what it means to learn a concept, not example. How many of these can I have? Absolute 1 over x, absolute, right? I can have them all. It's better to know the concept of how to obtain something than to learn. Over here, I gave you 15 graphs. Is it better to learn one concept or to learn 15 examples? One concept is better, because you can generate all of these answers from that one concept of taking something. So that is your first step in being successful in calculus. Learn concepts rather than examples, because the concept you learn will be applied to all of these. Great. The next part is a piecewise function. And we have few of those.
So piecewise, all the functions we did kind of piecewise functions.
So yes, so each one will be in its own neighborhood, let's say that way. Let's say that I have f of x is equal to 3 for x less than 0, x plus 1 for 0 less equal than x less equal than, let's say, 2. And then let's say we have negative x squared for x larger than 2. So how many pieces does this function have? 3 pieces. There are three lines, right? Like 3 lines of code. So there are 3 lines, there are 3 pieces. Now this over here shows you the partition on which these individual functions are active. So to graph this, I will draw coordinate system, and then I will put these partitions lightly, which are happening at 0 and 2. What I have done is I partitioned my space that goes from negative infinity through 0 through 2 to positive infinity on x-axis. So now my constant function 3 is active up to vertical partition 0. So I get to draw constant function 3, an open circle on y-axis, which is 0, because there is no equal sign on this one. In the middle partition, between 0 and 2, I get to draw x plus 1 linear line. So that's going to be using these filled-in circles at the 45-degree angle. You can see that when you plug in 0, you start at 1. And then when you plug in 2, you end up at 3. And then you connect with a straight line. And then we have negative x squared. Now, where's that? Well, that's going to start at the vertical line 2 and go on forever. So 2 squared, that's going to be a negative 4. Open circle at negative 4. And it's going to be a parabolic drop down. It's not a straight line, it's curved line. Parabolic drop down. Where is your parabola? Your parabola would be like this. That's terrible. Your parabola would be something like that, right? That's what your parabola is, but you don't need this piece, because that's the piece where the linear line lives and the constant function. You can't have them all. You are not allowed to stack these functions one on top of the other. You are not allowed to have two filled-in circles one on top of the other, because what? Uniqueness, exactly. Uniqueness. The word unique allows you to only have one y value for any given x. So if I have two black circles on top of each other, then for that x value, you would have a black circle here, black circle there, not unique, not a function anymore. Right? So it's very important to have those concepts clear. That's where the uniqueness kicks in. So if you see equal sign, that's where you fill in the dots. When you see no equal sign, like x less than 0, then you have the open circle for that. Can we have exponential, logarithmic, trigonometric functions in this mix? Yes. Is that hard? Is it annoying? Sure. There's a difference between hard and annoying, right? So, what happened?
I'm barely keeping up with this.
Well, we're reviewing, so it's kind of going fast. But you can always rewind. That's why I'm streaming. So you can go and you can press the button to get it to any speed. Exactly. All right. We know what the function is. We know what the major players are. Now we know what they look like. We also know, now we need to know transformations. There we go. I couldn't remember the word. We get to shift this left, right, up, down, reflect them and flip them, and the whole spiel of mathematical gymnastics that we can do. So what are the flips? We have f of x plus minus c. This would be shift up or down. Then we have f of x plus minus c, which is shift left or right. We can stretch or shrink functions by cf of x or fcx. Stretch, shrink. And finally, we can have negative f of x or f of negative x. Reflection on y-axis.
So which one would shrink? Would be f of cx?
For what?
Which one would stretch the function?
Depends on the function, so we'll have to talk about it. Reflection on... No, I got the... Sorry, the top one is x-axis, this is y-axis. There we go. I can't multitask. Just one task at a time. I'm like Intel processor. Yeah. It's no multi-threading like AMD, like 70,000 cores. You seen those things? People still buy Intel. Amazing. All right. So now, what do we do with this? Well, you get to see y equals e to the x minus 2 plus 3. That was a good effort. So now what? What's the way to graph this? Well, we start with the original e to the x, because there has to be an anchor point somewhere that you are able to shift around. So for original e to the x, I should be sitting down for this one, but such is life. So for original e to the x, your anchor point is this 0, 1 that the graph goes through. Okay, now I have 2 shifts up there. What is the plus 3 going to do? Yes, that one is going to be up 3.
That 0, 1 is going to become 0, 4.
Perfect. And then what is the negative 2 going to do?
Right.
Yes, 2 right. So, as you said, the point 1 goes up to 4, and then we go over 2 units to the right. And you draw the same shape. So now, 1, 2, 3, 4, 1, 2. The horizontal asymptote that was at the x-axis is now moving to go through 3. Everything moves up 3 units, guys. We had the horizontal asymptote at 0. We are moving up 3 units. Horizontal asymptote goes up 3 units. So we follow and then go through. We label this point as 4, 2. And we win. That's it. All of your functions will behave the same way. Some of them have anchor points that you get to shift. Some of them only have asymptotes that you get to shift. Some of the more popular functions for calculus would be those rational functions, like y equals 3 over x plus 5. So this one is coming up tomorrow already for graphing. And I hope you will practice without a calculator. I mean, anything you do, you should verify on a calculator just to make sure that you're doing it correctly. You have access to the computers. You can use Desmos. You can install graphing apps on your phone, as I mentioned, right? So graph, and then verify that you are doing these things correctly. So you're happy. What we have is our basic 1 over x. That's what we have, 1 over x. No anchor points, right? All I have are two asymptotes that are intersecting at 0, 0. Intersection of those points will help you with the anchor, right? So we can write and understand this function as y equals 3 times 1 over x plus 5. So this 3 is a vertical stretch. And plus 5 is what?
Oh, let's say it's going to shift it.
Where? Shift left 5. Nice. So plus is going to shift left. Great. So (1, 2, 3, 4) negative 5. I do not have vertical shift, so the other asymptote stays at x-axis. The vertical stretch is just going to make the whole thing skinnier. It is not humanly possible to do, those shifts perfect, unless you're talking trig functions, then yeah. But for these guys, not so much. And that is the way to shift functions. Since we are out of time, I still need to talk about function composition, function combinations, and inverse. We will deal with that at the beginning of the class tomorrow. I would encourage you to read ahead. Sections 2, 2, 2, 3. Those will be definitely covered tomorrow. And then there will be. Now, is there a homework assignment? Yes. Homework assignment are review exercises from chapter 1. Chapter 1 in your textbook that is for this class is review of pre-calculus, which is all of the stuff we talked about so far. They have 52 exercises or more, I believe it's 52. Try to do one exercise from each cluster to see those concepts, and if you have any questions, obviously bring them in tomorrow, and we'll finish this tomorrow and then start limits, start calculus. See you tomorrow. Bye.